Welcome to EDU World Space.
Is to take the equation of an ellipse in polar coordinates, and with a little bit of dynamics and some understanding of mechanics, we should be able to come up with a conservation of energy equation. So the idea is we want to determine the components of the velocity of this object undergoing the elliptical orbit. We want to express that in terms of its polar vector form, which has both a tangential and a radial component. So realize that the r dot goes along the radius of the motion. The r theta dot is tangent to the motion. So let's just kind of draw that out in a picture. So here's an elliptical orbit. There is a focus somewhere. And we have the r hat direction, and we have the theta dot direction that is perpendicular to that. And we are expressing the velocity in terms of both components in this system. But what we are after then is to find v squared, which is kind of, it's not quite the kinetic energy, but it is related, which will be r dot squared plus r squared theta dot squared. Okay, so we can see that basically what we need to do is take the derivative of the r with respect to time. And once we do that, we are going to have basically both components. We can represent both components in some way with that, as well as with the r as a function of theta. So let's see if we can take that time derivative. It would be a times 1 minus e squared. And then we have to take the derivative of the denominator. That would square the denominator. And then we have to do the chain rule and take the derivative of 1 plus e cosine theta with respect to time. And that would be sine of theta negative times theta dot. And a couple positives cancel out, and there's an e there too. Okay, so I'm going to actually write this in a slightly different way. We're going to group terms that look like r, and so I will be replacing sort of a complex looking thing with r. Just it'll make life a little bit easier once we get into some of the dynamics. So I can kind of break apart that derivative into a part that looks like r and a part that is new. We'll put it that way. So looking at my v then, my r dot looks like r times e sine theta, theta dot over 1 plus e cosine theta, r hat, plus r theta dot in the theta hat direction, the tangential direction. And I can see that there is some commonalities between those two. We have an r and a theta dot in both of those. So I can kind of group that out. But the radial direction looks a little bit more complicated, as we can see. Okay, now that doesn't look like anything mechanical. It looks mechanical, but not anything orbital related. So we're going to bring in some orbital dynamics so that we can get some parameters in there. And what we know is by definition, the angular momentum is equal to m, well, it's actually equal to r cross p, but we have just the r and the tangential velocity involved in that. So those are perpendicular to each other. U, by the way, is what's called the reduced mass, just to remind you, is it's if you have two orbiting bodies, M1 and M2, and they're sort of close together in mass, that they're sort of undergoing a mutual orbit, and you have to use the reduced mass for that. But we'll see that that is not such a big issue. So that we can replace the theta dot in terms of the angular momentum. But furthermore, we want the period in there. So this next relationship comes from Kepler's second, integrating it over a full period. The constant angular momentum is 2 pi over the period times a times b times mu. So remember, a and b are the semi-major and minor axes, and p is the period. And that is a very nice thing to have, as we'll see, because we can simplify things in terms of g's and m's when we have the period in there. Yeah, that is helpful. So kind of putting this together, what we have is theta dot can be replaced with L over mu r squared, and furthermore, L can be replaced in terms of the period. So theta dot can be written in terms of the two axes, semi-major and semi-minor, as 2 pi ab r squared over the period. And this is kind of a generalization. So if this were a circular motion, recognize that theta dot would just be 2 pi over the period. But here, because of the elliptical nature, we don't just have 2 pi over the period. We kind of have to take care of the fact that we have non-equal axes. And this will do it. Okay, so yeah. So now we can express our velocity in terms of the period epsilon, not epsilon, the eccentricity, we'll call it that, and the semi-major, semi-minor axes, and r. And we'll have one more relationship that will be nice to relate the b to the eccentricity. But we'll go ahead and write down what we have so far. V is equal to 2 pi ab period. Let me make sure I'm getting this right. And the r cancels. One of the factors of r cancels. So yeah, okay. So going back up, we had r theta dot. So we need to multiply through by r. And then we have the usual. the usual parentheses. And I will make a note that B, if you're worried about B being in there, B can be related to the eccentricity through B over A. That ratio is 1 minus the eccentricity squared with a square root, kind of a Pythagorean theorem type thing. So now we're ready. We've got, and remember, if you're worried about the R being in there, the R is a function of eccentricity and theta. So yeah, it's all in there. But now we want to take V squared, and basically we're taking the square of the sum of the squares of the two components. So Pythagorean theorem again. And the stuff out front squares itself. And the parentheses get a little bit crazy, but not too bad. Okay, so the real problem is the stuff in the parentheses, and we're going to play around with that a little bit. We're going to take a little magnifier glass to the parentheses, and we're going to find a common denominator and see what this simplifies, if we can simplify it. So we have e squared sine squared of theta plus the binomial. And then we have found a common denominator. It's usually what we wind up doing, even though that's algebraically kind of a mess. And we can expand out the binomial. We will wind up with a epsilon squared eccentricity squared times sine squared plus cosine squared, which is nicely 1, plus a 1 squared, that's an easy one, plus 2 e cosine theta. Okay, so, and then I am going to do something a little bit interesting. We are going to add 1 and subtract 1 from the top. And that is so I can combine my 2 e cosine theta with something, which may not seem like a good idea, but we'll see why this is a good idea. I'm going to break up the terms now. And now you can see why I did the combining the way I did, is I get part of the denominator to cancel in one term, and the other term I have 1 minus the eccentricity squared, which I recognize as being related to B, and I'll mess around with it a little bit more. And that should have been a squared there. But I will cancel one of those squares, one of those factors. Okay, now it may not seem very simple, but remember, I am trying to relate some things back to R. Whenever there's a 1 plus e cosine of theta, that is essentially related to R. Okay. So I'm now going to simplify and say that R, and the reason I can do this is I want to group the R part separate from the cosine theta part. Okay, so I can further reduce this term to R squared over A squared 1 minus E squared squared plus 2 R A 1 minus E squared. So what I'm basically doing is substituting my 1 plus E cosine theta in the denominator with R over A times 1 minus E squared. And yeah, things are starting to look a little bit nicer. And so the stuff in parentheses actually reduces to the following. 2 over R times A. And now I have my substitution on my eccentricity is B squared over A squared minus R squared over A squared times B squared over A squared. Yeah, and we can further reduce that. There's a B squared in both denominators. Okay, so that is all in the parentheses that I started with. That was a lot of work. But now I can multiply by the outside. And one of the nice things that will happen is the B squared will disappear. And that is very nice. So let's go back to the beginning. B squared had a bunch of stuff in the parentheses out front. Let's call that the parentheses out front with a round parentheses. Okay, this is kind of a lot of algebra, I know, but there's some good physics in there. Divided by P squared, R squared. And if I carry through, what I notice is that the B squared cancels on both terms, which was really making me happy. And if I pull the R squared in as well, then I see I've got something fairly simple to work with. Is there two terms? There's one that goes as 2 over R, and the second one just goes as, let's see, that just goes as 1. Yeah. So the first term, yeah, there's still a 2a in the numerator. Yeah, and the units work out. So everything within that parentheses is unitless. I'm feeling pretty good about this, but there's one last step that you could take in order to see that this is energy conservation, and get sort of a nice relationship. This is a perfectly good relationship, but to work it out even further, we can use Kepler's third law. at least the fancy form of it, that the p squared is 4 pi squared a cubed over g times m1 plus m2. Okay, and if we put that into the equation, what we basically find is that v squared reduces to something a little bit simpler. And I'll leave out some of the algebra. It works out quite nice, but 2 over r. The a's cancel in the first term, and in the second term, we just get 1 over a. Okay, so really the hardest part was figuring out what to do with all the eccentricity and the theta dot, and keeping track of the powers of r, more or less. So kind of a lot of algebra, but there was some nice physics in there.